previous talks, we have heard a lot of your results, but it seems to me that you are not going to come back to old result, but it will be something new. Okay.
Yeah. So okay. So first of all, thank you for the invitation, and as you said, one would expect from me to talk about CI groups, but I have to admit that I have a joint project with Misha Muzicuk and Grigory Viabov and István Kovács and Peter Pálfi, but I believe that we've already heard two of these people talking about CI groups, and I decided to talk about something different. Especially, since we are the five of us, I don't feel my contribution like big enough to talk about that project. So, and obviously I wouldn't want to talk about old results. So I will talk about something different that I've already talked about maybe 3 years ago in BLAD, but then a lot of things have already changed. So I will talk about Fuglede's conjecture, and this is a joint work with Gergely Kisromanos, the molecules, and Máté Vizer. And so the motivation comes from a totally different area. So it comes from analysis, and so I will talk about in the first slide mostly about subsets of the Euclidean space of positive measure. So take a subset which is of positive measure, and I will say that it tiles the Euclidean space. If almost it just covers almost the whole Euclidean space, it means that the intersections, the parallel intersections, can be of positive measure, of zero measure, and the holes can also be of positive measures. And there is another property which basically says that you can do Fourier analysis on the set. That if you take the set of relative functions on the set, then it is spanned by orthogonal exponential functions. So pairwise orthogonal exponential functions. So there is a basis of these type. Okay, and the original conjecture that I will not talk about, I will talk about discrete case of this conjecture mostly, is the spectral sets are of positive measure are exactly those sets that tile. So that was the conjecture of Fuglede, and immediately I will change to finite abelian groups. So if you look at these definitions, so if you look at the first definition, then you just have to forget about these sets of measure zero. So the digital translates of the set has to cover the set. And spectrality, in order to talk about spectrality, you just have to give a notion to exponential functions, and in this case it will be characters, so irreducible representations of the group, which are obviously of dimension 1. And in this case, I will say that these representations are the spectrum for T, and I will denote it as a spectral pair. So it will be T will be the elements of the group, and these will be the elements of the representations. But representations can be identified by group elements since it's a finite abelian group. So basically, both of them can be thought about, and we can think about both of them as the subset of the original finite group A. So we can switch, and the interesting thing is that in this case we will also get a spectral pair, which also and it is also easy to see that the size of these two sets are the same. And obviously we can talk about the two different directions of the conjecture. So the tile spectral direction means that I know that the set is a tile. Do I know that it is spectral, and there is the spectral tridirection I will talk about mostly during this 30 minutes, and this is what we know. So it's so obviously R is not a cyclic group, but this means that the tile spectral direction of the conjecture for R, but in this continuous case, is exactly the same as the tile spectral direction for to hold for Z, and it is not extremely hard to prove that it is equivalent to the tile spectral direction of the conjecture for every finite abelian group, finite cyclic group. That's what I mean by this notation. So on the other hand, the spectral tile direction is not that nice, or the current state of our knowledge that is only that we know that the spectral tile direction of R implies the spectral tile direction for R, and it implies the spectral tile direction for every cyclic group. But we don't know the conjecture, so we don't know whether it holds. So it's still open. So first of all, I would like to say what we know about these groups. So not too much. So as you may see that But these are the cyclic groups that we know that the conjecture holds, and there is no counterexample. So as you may see on the list, so that's not really too much. So it's like so the number of prime divisors that appear in the order of this cyclic group is at most 4. So this is our recent result, and okay, so the exponent can be larger, but we still don't know too much. So it's widely open. What about elementary Wheeling group? So the importance of elementary Wheeling P groups is that the original conjecture refers this group by Tau, who actually defined or who actually first looked at the discrete version of this conjecture, and he constructed a spectral set which is not a tile. So how do you verify that something is not a tile? So if it's a subset whose cardinality does not divide the order of the group, then it cannot be a tile. That's obvious. And on the other hand, what does it mean that a set is spectral? So if you look at the character table and you take the rows corresponding to S, which is a subset, and you find the same amount of representations, and that the induced submatrix will be a Hadamard matrix if these representations form a spectral set. I mean, it's just a reformulation of this orthogonality condition. So obviously, I mean, okay, so if E is 2, then it will be a Hadamard matrix. Otherwise, it will be a complex Hadamard matrix, since the numbers that appear here will not be plus minus 1, but roots of unities. Okay, so that was the first observation of Tau, who actually disproved the conjecture in the discrete case, and he lifted up to the continuous case as well. So the conjecture actually is only open in dimension 1 and 2, and for the elementary VMP groups, we know that the conjecture does not hold for rank 4 elementary VMP groups, but it does hold about for rank 2 elementary VMP groups. I will talk about it later on. And it is basically open in ZP3, except for really small primes, but they are really hard to prove, even for these small primes. And we wanted to solve this case, we wanted to prove it, and we could not succeed. So instead, we actually proved that ZP squared times ZQ is a group such that the Fuglede's conjecture holds for these groups. But in this case, we have to assume that P and Q are different primes. Otherwise, we would solve the previous problem, which is not the case. So and in the abstract, I promised that I'm going to talk about some of the methods that we are using, and one of them is this inductive approach. So first of all, you would like to know that the conjecture for, I mean, so if you want to prove the conjecture for one particle group, then you want to know these for all the conjecture for all the subgroups. So this is one of the assumptions that we know that we will keep, and obviously we assume that 0 is contained in the tile and in the spectral set. You just translate your tile. It will not change the property that it's a tile, and also the orthogonality will not change. And if T or lambda has a very rigid structure, so it's a union of ZP cosets where P is one of the prime divisors of the group, then P is a tile. We know it, and this is really the inductive approach. So if P does not really generate, it does not generate the group, or lambda does not generate the group, then P is a tile. So that's one approach, and what are the exponential functions? So the exponential functions in this case are irreducible representations. So, and as I've already mentioned, the irreducible representations in this case form a group which is isomorphic to the original group. So the representations can be indexed by the elements of the group. And what does it mean? That they are orthogonal? Their restriction is orthogonal to T. So it means that if you take the representation which corresponds to the difference of these two group elements, then it vanishes on T, which means this formula. Okay, so this sum will be 0. And if you look at it, this is nothing else but saying that the corresponding eigenvalue to this representation of the adjacency matrix of this Cayley graph KGT is 0. So it just simply means that if you have a large spectral set, then the 0 is an eigenvalue that has a large multiplicity, a really large multiplicity actually. And from now on, we will just think about representations as the compositions to functions. So chi 0 is a representation. It is a composition of a projection P, and then to a cyclic group, and then the natural embedding of the cyclic group to the multiplicative group of the complex numbers. So chi 0 is just a faithful representation of a cyclic group. This is how every representation works for abelian groups. And then we are here. So I will. So let omega be an element of a group ring. So this is, I mean, this might show you that we are approaching Schur rings, but it's still far from here. So and I will define the mass polynomial of this element of this group ring. So this is going to be a polynomial that looks like that. So here it has the variable x, and I take x to the g. So and g is taken from cyclic group of order n. So the only way to that I wanted, I mean, so it has to make sense. So this is not really a polynomial in zx, but this is a polynomial in zx quotient x to the n minus 1. So you have to factor out by this ideal, otherwise this exponent does not make sense. But if you just take a subset of zn, then it then what you get is this one. So the characteristic function of t will be the sum of the elements of t, and then the mass polynomial is just this one. So if you go back to the previous page, then what does it mean that that chi vanishes on t? So it just simply means that xi is a root of this mass polynomial of t, where the order of this so this is a case primitive case rules of unity if the order of this representation is k. Okay, so this is a reformulation in terms of polynomial of this property, and this polynomial is of integer coefficients. This can be translated into the fact that phi k, where k is the k cyclotomic polynomial divides MP. And this is what we are going to use. And here's the theorem, which might be considered the focal theorem, but we proved. We also proved it, and I will say it in a strange way. So obviously a cyclic group can be written as a direct sum of cyclic groups of prime power order, and then you take an element of this group ring, and then what does it mean that phi n divides the m omega? Then this mass polynomial, then it just simply means that m omega can be written as the weighted sum with integer weights of characteristic functions of z pi cosets. So these are the prime divisors of n pi that appear here. So you take a coset, you get some weight, and you can add them. This is how you can obtain the characteristic function of omega, or this is, I mean, or this weighted function of on the points. So, and this is a really nice description, and the proof is actually extremely easy if you find the right approach. But it has a very innocent-looking consequence that we call cube rule, and I'm going to try to explain what it is, and I'm going to try to apply it. Also, so what does it mean? So in this case, the setting is slightly different. So n is going to be a square phi integer. So Zn is the direct sum of cyclic groups of prime order. And then what is a cube? So you take two element subsets of ZPI, and for each ZPI, and you take the Cartesian product of these elements. So this is just a subset of Zn. Okay, this is how this is basically a cube, and then you sum up all these elements. Then you take the alternating sum of the weights appearing in the cube, and this is the Hamming distance. So you fix one of the vertices of the cube, and then this is the Hamming distance of x from this vertex. So if it is odd, then it will be a -1, and if it's even, then it will be a +1, and you take the sum, and it has to be 0 for every possible cube. This is what Cn divides the mass polynomial implies. So this theorem can be translated to this innocent looking, and maybe it seems that it's hard to use this condition, but I will try to use it. Okay, so what about representations of prime order? So what does it mean that a representation of prime order vanishes on P? It means that Phi P divides the mass polynomial, which implies P divides the cardinality of P. This is, again, a very simple observation. So if you have a spectral set and you have two elements in a Z picoset, so whose Hamming distance is 1, and they are contained in a Z picoset, then it implies that a representation of order P vanishes on T, then it implies that P divides the cardinality of T. So this is how we are going to use it, but we'll mostly use it indirectly. So if P does not divide the cardinality of T, which is equal to lambda, then there is no pair of elements with lambda, which only differ in their P coordinates. So they are contained in a Z picoset. This is what is excluded. And this is also excluded for T because lambda T is also a spectral pair. So if you switch the role, then Hamming distance 1 in a particular direction is excluded. So that's the strategy, and then how we are going to use it. So the thing I'm going to use it for is that I'm going to prove a result of Xi that I've already mentioned. So in this case, T is a spectral set in ZPQR. So in this case, you have 3 different primes, and she proved that the conjecture holds for this group, and I'm going to prove half of the spectral tie direction. So I'm going to assume that T is spectral, and I'm going to assume that phi PR divides the mass polynomial of T. So this is one case, and the other case that phi PQR does not divide the mass polynomial. So then you need a different type of treatment. So and then I say T is a time. So what is the proof of this statement? So first of all, you have to understand what happens if 2 of the primes PQR divides the size of T. Then you just simply project. There is a natural projection to the subgroup ZXY. So you simply project T to this ZXY. So there are 2 different things that can happen. Either the projection covers the set once, covers the subgroup once when you have a tie, so it's naturally a tie. So if you add the ZR, so if you add the subgroup to this set, then you obtain the whole group. So you have the direction of the projection. If there is exactly 1 point in each of these cosets, then it's a tie. And otherwise, if it is not the case, then there are 2 elements that project in the same point, but their Z coordinate is different, where Z is the 3rd prime. So it would imply, using the previous observation, that Z divides the size of T. And then we are done because then X, Y, and Z divides the size of T. So T is the whole group. Okay, so this is the first case, and the second case where I'm going to explain how I use the cube rule. So I hope I will be able to share my whiteboard. So this very innocent looking thing I'm going to explain to you. So assume that you have a set T, which is a spectral set, and 2 of the primes among P, Q, R do not divide the coordinate of the set. So then you have a point. I mean, assume that you have a point here, and this is the P direction, this is the Q direction, and assume this is the R direction. So these are the subgroups ZP, ZQ, and ZR, and this is how you imagine your group as a direct sum of elements. So since P does not divide or Q does not divide the coordinate of T, I know that there are no points of set T, and I know that there are no points of set T here. And assume that in these particular points, this is not included in T. Okay. So in this case, I can see that the Hamming distance, the points of Hamming distance 1 from this point are not contained in the set. So and since all the sums on the vertices of every cube is has to be 0. So it's like so there has to be something in T in my spectral set T of odd distance from this point. But the unique point in this particular cube is this one, which is of Hamming distance, which is of odd Hamming distance from this point, because these are excluded. Okay, so this innocent looking condition would imply that this one is contained in T. And since you can choose your cube however you want, you can choose another cube whose vertices are just the replacement of these points to this one and this one to this one. And the same argument will imply that this one is also contained in T. But then you have 2 points which are in T which are excluded, simply because they are contained in a Z picoset, which would imply that P divides the cardinality of T. So this is the very simple proof. Using the condition that you can find an element of which such that this one is here, and in this same Z arcoset, this element is not in T. So it implies that if you have a point here, then everything that is contained in this Z arcoset is also contained in T. So if you go back, so if you go back on the slides, oh, I hope I can move it again. So if you go back on the slides, then you will end up here in this thing which is called reduction. Sorry, I was too quick. So here this reduction. So if either T or lambda is the union of some Z picosets in this case R plays the role of P, then it is a tile. So we just proved the half of the theorem of Xi, or maybe even smaller part, and then this is one of the techniques. But there are recent improvements as well. So there is this new technique that I'm trying to explain here. So this is based on Schurings, or this is a computation in group algebra, but the idea is the following. So if you want to count with elements, then it will be really hard to prove anything if you just calculate in the group algebra, because then you have too many elements, then you have too many coefficients there to count with. So you just want to basically to reduce the number of equations that will appear at some point, and so you basically just average out, and the averaging out technique is something that I will not explain to you. I will just say that we have this theorem that helps us solving our questions. So let G be a finite abelian group, and S lambda a spectral pair in G. And then what is A is going to be a natural cyclotomic Schurring induced by the following automorphisms. So you take x to the k, where k is prime to G. So so the orbits of these functions will be the basic sets of in our case. So here we have the basic sets of our Schurring. And then I define this number, which is going to be a rational number in this case. So I basically average out the elements of S on all of these basic sets. And then the theorem is the following. So there are non-negative BIs, such that here's an equation. Okay, so I should have an overline here. So these are the basic quantities, which are the sums of the basic elements. So I have these AIs defined here. No, sorry, I don't know what happened. So here I have these AIs defined above. Here I have these XIs, which are the basic quantities, and I would like to find VIs with the following properties: that they are non-negative, and one of them is and V0 is 1. And the theorem says that if you have a finite abelian group and S lambda is a spectral pair, then there is a solution of this equation always. And how do you use this thing? I'm going to apply it to reprove the results of Iosevich, Majeli, and Pakianathan, which says that the Fuglede's conjecture holds for ZP squared. So you take, I will only prove the spectral time direction. So what are the steps? So first of all, I take a spectral set, and since every non-trivial representation in this case is of order P, we can see that P divides the coordinate of S. Okay, so and then you use the equation. I'm not going to explain it how. I'm not that if the size of S is larger than P, then S intersects every non-trivial basic set in the same amount of elements, which if you combine it with the fact that P divides the coordinate of S, then it will simply show you that S is the whole group. So this is one of the arguments that we've gone through many different times with István, for example. And I'm not going to prove the case when S is P, so it's just yes. Yeah, so that's it's actually the S equals P because it's not really interesting. This is the hardest case, and actually this is our second proof that we found for this theorem. But I just wanted to highlight I just wanted to mention that the Schurings can also be applied in this topic, and I think that's how I would like to end my talk. So thank you for the opportunity.
Okay, thank you very much for your talk. And are there any questions to Gabor?
So may I ask, maybe
sure,
it's very stupid question. Are there some statements like, for example, if some Schur rings satisfy some properties, then the conjecture is true for our group? No? Maybe some criterion via Schur rings to check the conjecture for given group.
So this is so it would be so this was the only equation that we could produce from Schur rings. So we wanted to extend and get more Schur rings and get more equations. But this is the only one that makes sense from the point of view of the conjecture. So I think no. The answer is no. But I mean, we wanted to create more, but we just didn't succeed. So.
But is it possible to create more equations? Yes, of course. For like in the same way of produce more equations. Yes.
You can if you have some assumption on the cardinality of S. Then you can produce more equations. But then you have to handle the Schur ring separately for different S. I'm not saying that it's a bad option, but so you could have more raising to the power if you would assume that S is not divisible by. Okay, so
thank you so much.
Okay, are there any other questions? Well, then I just wonder, how did you get this idea to use Hamming distance in your cube rule technique?
Hamming distance.
Yeah.
Okay, so I mean, if you go back to this, so we were, so actually there is this theorem here, and which I mean, let me, or maybe not. Maybe I'll explain it into a whiteboard because it's easier. So if you look at your group as the direct sum of some other groups, then and you have subgroups, then you basically think about subgroups as lines or planes in this situation. And if you take the sum of these, then you can easily understand that the sum of these two elements will be the same wherever you take your subgroup. If you take this subgroup, then the weight of this subgroup on this point will be 0. So this was the observation that we have to reformulate it in some way, and Hamming distance of these 2 points is just 1, So, and the weight is the same. So if you give this sign here, then it's a very natural thing to think about.
Right. Yeah. Mm-hmm.
Yeah. So that's how we actually found this rule that to apply this theorem, because it makes understandable this theorem.
Yeah. Right. Yeah. Yeah. That is true. Yeah. It was so easy to see how it works. Yeah, but it is not so easy to find, I think.
Thank you.
Yeah, okay. Thank you.